Swayam Prabha. Digital India. Educated India.
Hello again. Welcome to this module on basics of noise and its measurement. In the last module, we had discussed about the decibel scale, octaves, and important terminology related to acoustics and noise. So what we are going to do today is figure out how do we add decibels. What does that mean? Suppose I have one particular source of noise and I have another particular source of noise, and let's say the decibel level from one source is L1 watts, L1, and another source is L2. And then if I play both these sources together, what will be the overall sound pressure level in the room? This is what the question is going to be, and things related to that. So that's what we are going to discuss in today's lecture. So let's look at the definition of decibel once again. So if we are talking about the sound pressure level, that is LP, then it's defined as 20 log, and when I say log, it's log on base 10, 20 log of P, which is the pressure, RMS pressure, divided by P naught, which is the reference pressure, then in decibels. And the reference pressure, if the medium is air, is 20 micropascals. Now, at this stage, I wanted to make one important clarification, that this P here, which we are talking about, is the value of RMS pressure. What does that mean? Suppose this is my pressure level, and let's say I am measuring and let's say this is my pressure recording. Okay. So when I am going to compute decibels or LP, the question is, so this is the formula, P over P ref. I take the log of it on base 10 and then multiply it by 20, I will get pressure. So the question is this the value of pressure, or is this the value of pressure? So which pressure I am going to put in this formula? And the answer to that question is that this pressure is actually RMS value of the pressure. Okay, so that's the RMS value of pressure. How do I calculate its RMS? Well, what I do is that I discretize, I break this data into small points. Okay, so this is P1, this is P2, this is P3, and so on and so forth. Okay, so I break it up into a very large number of points, and suppose I want to calculate the decibels corresponding to this whole time period. So I break it up till I get to this time period and say, let's say this is Pn. Okay, so RMS stands for root mean square, and that's how I am going to calculate the value of RMS. So what I will do is, first I will take square, so P RMS. First I am going to square up all the pressures P1 through Pn. So I have done the square thing. Then I am going to take the mean or their average. So I will divide it by n. So then I have taken the mean also. And then I am going to take the square root of this entire thing. And that is the value of P RMS. So it's important to understand that if I have data like this and if I have to calculate decibels, I have to calculate RMS value of the pressure. That RMS goes into this formula. I divide that P RMS value by reference pressure, which is 20 micropascals, and then I use this formula to calculate the pressure, sound pressure level. Okay. And this is only for sinusoidal waves. For sinusoidal waves, P RMS is equal to P max over square root of 2. So it's important to understand that only for sinusoidal wave, the RMS value of pressure is maximum pressure divided by square root of 2. This factor changes based on the shape of the wave. So for this wave, it may be something totally different. We do not know. We have to actually calculate it. For a square wave, it will be a different value. For sinusoidal wave or a cosine wave, the RMS value is P max divided by square root over 2. So with that understanding, we will do these two examples. So suppose P is 1 Pascal. What that means here is that we are assuming that the value of RMS pressure is 1 Pascal, not the maximum pressure. So its RMS pressure is 1 Pascal. Then if I have to calculate the decibel level, then that's what I do, 20 log 10 P, which is 1 divided by 20 micropascals. So I get 20 log 50,000 and I do the calculation, I get 94 decibels of sound. In another case, P is 31.7 pascals. So again I calculate 20 log 10, 31.7 over 20 into 10 to the power of minus 6. And I do all the math and I get 124 decibels of sound. Now, it's important to understand at this stage is that in this case, the pressure was, in this case, the pressure was 1 pascals and we got 94 decibels of sound. In the other case, pressure was 31.7 pascals. So pressure went up by a factor of 31.7. But on the decibel level, the pressure went up only by 30 decibels. What these two examples show is that if the pressure is getting doubled on the linear scale, that does not mean that the pressure will also get doubled on the decibel scale. On the decibel scale, the pressures change a little slowly, but on the linear scale, they can change very rapidly. I mean, that's the whole point why we are using logarithmic scales. So once again, when we multiply pressures, if the ratio pressure goes up by a factor of x on the linear scale, it does not necessarily mean that pressure will also go up on the decibel scale by the same factor. So that is a very important point to understand. The next question is that suppose I have two motors or suppose there are two machines in a room and one machine is generating, let's say, L1 decibels and the machine is generating L2 decibels. And then I want to figure out that what if both the machines are running in the room together, what will be the overall decibel level of the sound. So how do we add it up? Now there could be three ways or several ways and three possible ways I have shown here. One is we add up dBs. So suppose there is L1 is 40 dB, L2 is 40 dB. Can I argue that it is 80 decibels? The second way is adding up powers. and then that gives me 43 decibels. And how do we get 43 dB? We'll see it later. Or do we add up signals or pressures? So there are several ways to add dB, but only one of the ways is correct, and that is what we are going to learn, that what is the right way to add up decibels. So this is a chart, and how do we get this chart? We will see it later, but what this chart shows is that you have two sources, source 1 and source 2, and let's say in first case you have source 1 at 120 decibels, source 2 at 120 decibels. Then what you do if you have to add these two up is you calculate, in terms of milliwatts, let's say wattages, and how much each source is emitting, and that is 1000 watts, 1000 milliwatts. The second one is 1000 milliwatts. So the total energy or the power which is flowing into the system is 2000 milliwatts, which makes sense. It is physically consistent. So then you use that 2000 number, this number, to calculate the overall decibel level in the room, and that gives you 123 decibels. Let's take another example. First source is 115 decibels, second source is 120 decibels. The wattage corresponding to the first source is 316.2. You back calculate it using the formula, and the wattage corresponding to the second source is still 1000. Total wattage is 1316, and from that you calculate that it's 121.2 decibels. So even though the wattage went up by 30%, and decibel scale the wattage went up by about 5 dBs. Okay, so this is something very important to understand. And what this chart shows is that if there are two sources, this is how they add up. And now we will actually do an example. So adding decibels with multiple sources, add powers, and do not add decibels. What does that mean? Suppose there are n sources, so the power emitted by ith source Wi is 10 to the power of L. L is the decibel level divided by 10 times 10 to the power of minus 12. So total wattage is, so this is how you calculate the wattage of ith source, and then you add up all the wattages, and then once you have done this, then you compute the total sound power level using this, and that's how it is done. Example, suppose you have a sound power level of source 55 dB and another source is 51 decibels, then what is the total sound power level of two sources together? We'll do that here. So you have, let's say you have a room, source 1 55 dB, is 51 dB. Then from here you calculate what is the power flowing out of this source. So W1 is equal to 10 to the power of minus 12 times 10 to the power of 55 over 10. How did I get this? I got this because I know that dB for power. So this method is for power, but if you have pressure, you can do it in the same way. So dB power is equal to 10 log of 10 RMS power divided by reference power. Okay, so I'm using this relation. I know this is 55. I know W ref is 10 to the power of minus 12, so I am calculating W using this formula. So it comes out to be 3.16 times 10 to the power of minus 7 watts. Similarly, for the second source, W2 equals 10 to the power of minus 12 times 10 to the power of 51 divided by 10 equals 1.25 into 10 to the power of minus 7 watts. So the total power which is being emitted if both the machines are running is W total. W1 plus W2, and so this is there. So LW total is equal to 10 log divided by 10 to the power of minus 12. I put in the values of W1 and W2 from here, and what I get is my final answer, which is 56.5 decibels. So this is how I add up two powers. So the answer is 56.5 dB, and the method has been shown here. So if I have two sources, I can use this method, and if we are talking about powers or intensities, I can add them up in such a way and get the answer. Remember, and this is based on all the calculations, you can verify it yourself. If there is an increase in decibels of 3, power increases 2 times and the pressure increases 1.414 times. If there is an increase in pressure of 10 decibels, power increases by a factor of 10, pressure goes up by 3.2. If increase is 20, power increases by 100 and pressure goes up by 10x. And similarly, you have on the negative side, if I decrease my power by 3 decibels, power becomes half, pressure goes down by 0.717. And it will be worthwhile for you all to do this exercise and prove it to yourself. How is this happening? Okay. Another example. There is a wall which attenuates sound by 20 decibels. And so there is a wall, there is a sound coming from here. Initially there is no wall, and I measure sound pressure level here. Let's say sound pressure level here is 180 and 90 decibels. If there is no wall, then I put the wall, and then the sound pressure level is going down by 20 decibels. So we say that the wall is attenuating sound by 20 decibels. That's the language. So if a wall attenuates sound by 20 decibels, and in absence of the wall, we can hear sound at 90 decibel level, what will be the sound level in presence of wall? So the answer is L with wall is equal to L without minus 20. L without is 90. 90 minus 20 is 70 decibels. Another example. A lathe is generating 76 decibels of sound, while a blower is generating 70 decibels of sound. What is the combined sound power level in the room? So this question is exactly same as this particular question, just the numbers are different. Instead of 55 decibels, you have 76 decibels. Instead of 51 decibels, you have 70. And you do all the math using exactly the same approach. What the answer you get is L total equals 10 log 10, 10 to the power of 7.6 times plus 10 to the power of 7 is equal to 77 decibels. So this is the other one. This is another question. The noise level in a machine shop. So you have a machine shop where lots of machines are running, and there is also one special machine, a milling machine. So when you turn off the milling machine, the noise level is 51 dB. And when you turn it on, the noise level is 58 decibels. So the question is, what is the sound pressure power level generated by the milling machine? And the answer to that is, so again, this may also be an exercise for you at home today, and that the answer is 57 decibel. How do you calculate it? You find the power level, the overall power level when everything is running, which is 10 to the power of 5.8, and then you subtract it from 10 to the power of 5.1, so you get the difference in power levels, and that is the power generated by the milling machine alone. So then you take the 10 log of that number and you get 57 decibels. Okay, so this is important. And lastly, I wanted to explain that if there are signals, so we are not talking about wattages, but suppose there is a pressure signal or velocity signal or acceleration. Now in case of sound, we are not talking about acceleration or voltage or velocity or force, but primarily pressure. So suppose there is a pressure signal, and then if we have to add them, how do we add them? So if we want to find the decibel level due to two individual signals, then we must first add them. So this is about signals, this is not about wattages. Then we must first add them and then find the resulting level. What does this mean? Suppose there is a speaker which is generating 1 Pascal pressure, and there's another speaker which is generating another, say 1.5 Pascals. Then in certain situations we can add them up. And when do we add them up? This is what it says. So what it means is, so suppose I have one pressure signal, okay, so let's say this is P1, and then I have another pressure signal, and I will plot it in dotted line. These two signals are known as correlated signals. What does that mean? What means is that there is a strong degree of correlation between each of these signals. In other words, when the dotted signal is becoming maximum, the solid line also becomes maximum. When the dotted signal becomes minimum, the solid line also becomes minimum. So there is a correlation between both the signals. Both the signals are dancing together. They are moving together. These are correlated signals. If there are two correlated signals, and if the pressure due to one is P1T and the pressure due to the other one is P2T, then the overall pressure I can calculate by adding up individual pressures. P1T plus P2T, that is my total pressure, and then I can take the RMS value of this signal, P total, and calculate decibels using formula 20 log 10 P total RMS divided P ref. Okay. So this is for correlated signals. Now I will do another example. If the signals are not correlated, so suppose there is one signal and then there is another signal so this is signal 1, this is signal 2, and both of these are not correlated. In this case, if we have to combine the effects of these two signals, what we do is we add up energies. And when I say energies, we can do that in an equivalent sense by adding up the squares of RMS. So what we do is we calculate P1 RMS and we calculate P2 RMS, and then overall dB is equal to, we use the original formula 10 log 10 and this formula is going to give us the overall sound pressure level. So when we are talking about signals, we have to figure out whether the signal is correlated or not. If we have correlation, then we can add the signals by themselves. If the signals are not correlated, then we have to square up the RMS values of those two signals, add them up, divide it by reference pressure square, take the log, multiply it by 10, and then we get the overall sound pressure level. So if it was wattages or intensities, we just add up wattages or intensities. If it is pressure, then that is what we do to calculate the answer. So that's what it says. Adding uncorrelated signals, this is what it says, and decibels add like power. So with this, we conclude this last module of the first week. I hope this has been a very productive week for you. And please review all the concepts which we did today, and look forward to seeing you in the next week. Thank you.